Right. Today we're also going to do motors and generators. So have a look at this cute little site we found. I just want to show you it. So it is called walterfent.de. And it's quite nice here because it shows, this shows you, it's got a little handle there and you're turning it. And look, this is a voltmeter. First, the voltmeter goes to the right, and it goes to the right again. So the voltage is only positive. So it's forming this. So now you've got to ask yourself, what type of generator is this? So here's the handle you're turning. You're inputting mechanical energy, and you're getting out this type of wave. So now we've got a little song. My split ring makes me behave like a DC wave, like a DC wave. So this is a DC generator. Okay, you can also change the direction of movement. Okay, it's still going clockwise. Oh, here we change the direction. So now watch what the voltmeter does. Now if you change the direction of movement, it's generating a negative current, and there we a negative voltage, and there you see the same pattern but below the line. So by changing the direction, we've got a DC voltage generated, but it's a negative voltage. Now watch what happens if we rotate it faster. Watch what happens to the size of those. Okay, so let's move the speed of rotation up. You see what happens to, first of all, those little bumps or crests get closer together, but also the voltage gets higher. And if we slow down the rotation, you see how low those crests are and how far they, in time, they spread apart, because this is time on this axis. And so obviously it's taking very long to rotate it even once. And by rotating it so slowly, you're getting such a small voltage. So that's how a car alternator works. As the car accelerates, the alternator goes faster and faster. The voltage wants to get bigger and bigger, but there's something inside the car's alternator which has to stop the current from getting, watch what happens, the current just gets too big. And the voltage gets very big. And you only want a 12 volt or 13 volt voltage in your car. So there's a piece of electronics there that keeps the voltage from getting too high and spiking. So now let's also do it without, this says with a commutator. Now this says without a commutator. Now look at that. Now it has got slip rings. So now we go. My slip rings make me behave like a sine wave, like a sine wave. And this is a sine wave is positive at times, negative at times, positive at times, negative at times. So this is an alternating current generator. So look at it. It's turning, look, we're turning that clockwise. Let's change the direction. So you don't really change the pattern even if you go into a different direction. The only thing you can do to change the pattern is really make it go faster or slower. There it's going slower, lower voltage again. And let's make it go super fast. And there's the fastest we can get it to go. And that's the biggest voltage, and it's almost going off our voltmeter. Lovely. Isn't that nice? Okay, so you can play with these simulators. It's fantastic. Looks like we still don't have a class today, but at least we've gone over a little bit of alternators and generators. I wonder if we're going to see them. So what I think I'm going to do is I'm going to go through some of the questions in our question paper. So let's go to preview. Let's share with preview. And let's find some questions, anything on, so we're going to be doing circuits. There's our equations. Current equals charge over time. EMF is work done per charge. Voltage is work done per charge. Here's your formula for resistors in series. Here's your formula for resistance in parallel. And here you're seeing batteries that have got internal resistance, and there should be a formula, EMF equals, normally written EMF equals I, and in brackets R plus R, but they just rearranged that formula. Here is work done in volts times amps times time. There should be a thing for power, is the rate at which work is done, or power is normally equal to volts times amps, but I don't see that formula there. Okay, so then we're also going to do motors, and you're going to use your left-hand motor rule and your right-hand generator rule to work on motors. And then they've got the mention that AC always uses slip rings and DC always uses split rings, or a commutator, a split ring commutator. So AC generator doesn't have a commutator. And then there's the graphs we see for one complete cycle. Okay, that's looking quite interesting. But now we want to go on to questions regarding anything to do with cells or with Doppler. So there we are. 3 light bulbs, X, Y, and Z, with resistance R, 2R, and R respectively. R, 2R, and R respectively are connected in a circular shown below. The battery has negligible internal resistance. When the switch is closed, all the bulbs light up. The reading on ammeter A is 2.5 amps. Which one of the following correctly describes the readings on the ammeters in amperes when bulb Z burns out? So A and X and Z were the same resistance, and Y was twice the resistance. Okay, so what you've got to know is that if you've got twice the resistance here than there, you're going to get half the current. The current here would have been the same as the current there. So which one of the following describes the readings on the ammeters when bulb Z burns out? So I know that when the bulb burns out, that you had 3 lots of current flowing, but there's going to be less current. So I'm looking for an answer with less current. It's going to be C or D. And then the readings on ammeter A is 2.5. Which one is one describe reading on the ammeters when bulb Z burns out? So the current's going to go down, and then I'm looking for A2 is going to have a smaller current than A1. That's got a smaller current than A1. So that has to be the answer, D. Okay, quite hard. You've got to actually quite know your stuff. So what's the logic behind it? Well, I don't want to mark it up yet, actually, to tell the truth. I want the learners to figure it out like I did. Okay. So the first thing we've got to look for is, yeah, you've got to kind of know, you really got to know your basics of electricity to do this kind of problem. Okay, so let's just go back to, okay, there we go. We have people waiting for us. Yay!